Good morning, folks. This is the second lecture of week 3, and today we're going to be starting the concept of shell elements, which are associated with surfaces. But before doing that, an issue comes up very frequently, and that is, are all finite elements the same? Formulations the same? The answer is no. There are two types of formulation. One is called the implicit formulation, and 90% of the mainstream application in finite elements basically fit that category. And of course, CATIA is of that type. The other formulation is called explicit formulation, and those involve, for example, problems which involve a heavy-duty contact, impact, explosions and things like that. And for example, abacus explicit, or Elastina, radius, and a few other ones are actually problems that have that kind of a formulation. Now, not all packages are capable of doing that, and incidentally, in all likelihood, and that used to be the case, but maybe that has changed. Explicit solvers, those which are primarily explicit solvers, such as Elastina, cannot do a good job on doing implicit calculations because they're not intended for that purpose. However, there are facilities within it that you can do some basic stuff of the implicit calculation. Why we're using CATIA here, or an implicit formulation, is basically we have to learn how to crawl before we start running. Okay? Now, on the agenda today, we have several items that we're going to be discussing, but let's start with the very first item, which is the concept of shell elements. Let me remind you that towards the end, I'm going to come and show you how to do problems of this type, which are not shells, obviously. This is a solid object, but you want to put for example, pressure on a particular patch here, or we want to apply a force at a particular location without doing too much work. Okay, I'm going to show you this, and the reason it pops up here is because for this particular pressure on a patch, we have to create a surface, and we are kind of concentrating on surfaces right now. So let's go to the business that we are dealing with. We have structures which are thin in one direction compared to the other two directions. And typical example is a pop can, pressure vessel, thin wall pressure vessel, maybe hood of a car, or a bathtub, fuselage of an aircraft, etc. In those situations, we're going to make an approximation in order to model these things with finite elements. If we try to put those solid elements through the thickness of this pop can, remember that's 0.5 millimeter, for example, then it's going to be a lot of elements that we're going to need in order to model the problem. So what we do instead, we take the surface of those objects, and we're going to put our mesh, which are not pyramids anymore, it's essentially triangles, okay? You can see that triangle on these surfaces. And we have to tell the software later on what the thickness of that particular surface is that you're dealing with. Now, shell elements which go on surfaces are either of linear type like that. So each node, just like a beam, has 6 degrees of freedom, 3 translations and 3 rotations. So 6 times 3 is 18 degrees of freedom in the global direction, okay? Now, the parabolic version of that, which is good for, they're more accurate than the linear, obviously, and it's good for approximating surfaces, curved surfaces, has, you can see that it has 6 nodes, and each node has 6 degrees of freedom. So that's going to be a total of 36 degrees of freedom that this particular element has. Here is the display, graphical display. Each node has 3 translations as unknown of degrees of freedom, and 3 rotations about the direction X, Y, and Z. Now, because these go on surfaces, obviously, you're going to need a surface. Now, those surfaces, the different ways of creating them, and this course is not making you an expert in surface design, but you have to know some very basic processes in order to calculate the surface of an object. And there are different ways of doing it. It could be that you have a 3-dimensional, for example, three-dimensional geometry, and that's given to you, or you create in CATIA, and you want to extract the surface of that object. That's one way, we call it extract. Or it could be, for example, you want to extract the mid-plane of a three-dimensional object. Let's take the case of the instrument panel of a car. Now, it's very thin. That's relatively thin with respect to other two dimensions. So it could be that the geometry was sent to you or you generated in 3D, and now you want to extract the middle surface of that instrument panel. Or obviously something you might approximate it with the outer surface or the bottom top surface or the bottom surface. Obviously, middle surface is more appropriate, but anyway, either way. So you take the three-dimensional object, you extract the surface of it. That's one way of doing it from the 3D solid object. Or it could be that the geometry was actually created as a surface. Okay, you don't have to extract. So you actually generate a surface somehow in using generative shape design, for example. And either way, at the end of the day, you need a surface. So obviously something gives in. It's just like beams. Beams are efficient elements for certain problem, but not every problem can be done with beam. And also something gives in. In other words, the results of beam are not as accurate as doing it with a fine enough, a good three-dimensional mesh. The same thing is true here. If you can model your problem in 3D, a good mesh, it will give you better result than shell. However, it may not be economically possible to do that. All right, so I'm going to do this problem for you a couple of different ways. For example, what we have here is a folded sheet metal, okay? And the thickness of this sheet metal is given to you as 0.1 inch. Dimensions are given, and the bottom of this edge is clamped, and the bottom and back edge is clamped, and the top face is subject to pressure. What we like to know is what are the stresses, what are the displacements, etc. The first thing that you realize is that this problem has two planes of symmetry. In other words, you can cut it halfway from the left to the right, like that, and you can cut it halfway from the front to the back. So instead of modeling this whole thing, you can actually model 1/4 of that sheet metal. But of course, you cannot leave these artificially created edges alone. I call it symmetry edges alone. The rules for applying symmetry conditions to those edges is exactly what you did for beams. In other words, find out what doesn't translate. Rotations are exactly the opposite of that. Okay, so the same rule that you use for beam element applies here to the shell element, and that should not surprise you because the degrees of freedom of a beam of a node at the beam element is the same as the number of degrees of freedom at the node at the shell element. Three translation, three rotation. It's not surprising that the conditions for applying the symmetry is the same. Okay, so the first time I'm going to do this is create this object as a solid object, and I have two choices. Either do the whole geometry here as a solid object. Basically, it's a box of size 4 by 0.5 by 2. That's one way of doing it. It's also because I'm doing a quarter of that, it's also possible to do this quarter of that box. So a box of the size 2 inches by 0.5 by 1. Okay, so let me go that route. We go here to the part design. So we go here, scroll down, part, and we say okay. Immediately I save this thing, file, save management, file, save management, save as, desktop, folder, new folder, I said solid, Oh, let me say shell element with the box. A box. Okay, good. Now, on that vertical plane, I will sketch a rectangle like that, size 2 inches. The length of it is 2 inches, half the length of the original shell that you see. This is 0.5. We say OK, exit, and pad it by 1 inch. Okay. So what you see here is actually a box of this size, 2 by 0.5 by 1. Okay, now this is made out of brass, I believe. It was made out of brass. So apply material. It can be steel, it can be aluminum, whatever it is. So metal, brass, on that part, we say okay. Good. Second. Now, we're going to go to the analysis and simulation, generative structure analysis. CATIA sees a three-dimensional object. By the way, we are doing static analysis. CATIA sees a three-dimensional object. It immediately meshes it with three-dimensional element. That's this. It immediately automatically creates a 3D property right there. But I don't need this. Okay? So I need to delete this element and I need to delete the property. I have to, first of all, get a surface here, but I don't have a surface here. So because, look, if you clicked on this and you tried, if you clicked on this and you try to take the box, it'll do it for you. Let me show you. It'll do it for you. But it does the entire box. In order to mesh that surface, it creates the surface automatically for you, but it does the whole thing. And I don't want that. So essentially, this becomes like a shoebox, a hollow box. That's not what I have. I have full sheet metal. So cancel it. Let me go back to my part design. And because I want to create the surfaces here, you have to go to generative shape design. Let me go from here for you. Start shape, generative shape design. And there is an icon called extract, and you'll see that in the operations toolbar. This operations toolbar is extremely important. Remember the join for beams? Remember that? We're going to need it here too. So anyway, but you expand this third one, you expand the third one, and one of them shows you kind of a box and an arrow pointing to it that says extract. You click on it, you select this, and you say okay, and do it again. You select this, and say okay. So notice what we have done is to create those two surfaces. The ivory color indicates that you have a surface. In fact, I can hide this box, put the cursor there, right click and hide it. You have a surface. You can see that. That box is in the background, is hidden. You cannot delete this box because the surfaces come from that box. But at least we know that we have created the surface. Now, before you go any further, join these two, because if I don't join it, later on I will be able to mesh this thing with shell element and mesh thing with the shell element, and because these are not joined, there will be duplicate elements along that seam. And there are ways to fix this. It's impossible to fix it, but I'd rather not discuss that right now. So you click on this, see that? You click on the join, you click this surface, here's extract one, and you click on that, here's extract two, and you say okay. Essentially, this kind of puts these two surfaces together so that when you mesh the top face, the side face is also going to be meshed. So now we're going to go back to the generative structure analysis. So here's the solid element that was automatically created. I deleted it. Remember, both the element and the properties. Here's the beam element. Well, this is not beam. So you click on the shell element, octree triangle mesh. CATIA calls it octree triangle mesher. Well, triangle. Think about it like that. It goes on surface. You click on it and you select that join. You see that? That surface. It doesn't matter what you pick. When you pick it, the other one is picked too. If these were not joined, you can do this, and then later you can do that, and they're going to be mesh, duplicate nodes and all that. But because I joined it, that's not going to happen to me. You click on that, and it says that you have linear element, parabolic element. This is the size. So let me keep the size like it is and show you the mesh. So put the cursor there, right click, mesh visualization, and the mesh looks like that. Okay, let's make this thing smaller. So double click on that. Instead of 0.2, let's make it 0.1. Okay, you say okay, and again activate, double click on this thing to do it for you. Then you can see that there's a finer mesh. Now don't let this thing bother you. You can hide the surface, put the cursor there. You can, oops, not the mesh. Let me see now. Let's do it like that. Let me hide this. So if it's bothering you, right click, hide and show, and there is no mesh, which is finer than what we had before. And of course, you have a choice of linear versus parabolic. When you look at it, double click on this, a choice of linear versus parabolic. I'm going to leave it as linear for now. Okay, so the rest of the problem, deactivate this. Now, oh, where is my part? The part isn't hiding. So let me bring it back here. Just the surface. Brought it back. Now, remember we had to specify the cross section of a beam. Now here we don't have a beam, we have a shell. We have to say what is the thickness of this shell. If you click on this, which is called 2D property, that makes sense. 1D for beam, 2D for surfaces, 3D for three-dimensional object, 2D property. Because we joined it when you select this thing, a default thickness of 0.1 is put on both of these sides, okay? So in our case, I believe this was 0.1 inch right there, you can see that, 0.1 inch. So I don't want 0.2, I want 0.1, and we say okay, and that's it. This thickness, which appears in your 2D property right there, you can see that. You may change this here if you want, but I don't want to. Appears in the tree of the properties. Okay, good. Now, the bottom of this edge is clamped. This bottom is clamped. You're told that. The bottom is clamped. And this edge and the edge back there, or depending on how you want to look at it, this edge and the edge here are lines of symmetry. If I go with this three-dimensional diagram, okay, so I do that edge and this edge. These are planes of symmetry, okay? So to do that, you have to go to user define, carefully uncheck everything. This edge is in the ZY plane, no displacement in X. You say ZY, no displacement in X. Rotations, exactly the opposite. See that? Because this is checked, translation is checked in direction one, rotation is left alone. These are unchecked, translations in these two directions are unchecked, so these must be checked. Okay, good. And the same thing on this side, except that things are going to be different. Let me uncheck all of these. So if you take that edge, that lies in the XZ plane, no translation in Y. XZ, no translation in Y. Rotations are exactly the opposite. Very good. Okay. Now, we have put a pressure up there, right? So we're going to put a pressure on that face of magnitude 100 psi. Please make sure you don't divide 100 psi by 4. So that's 100 psi. And if the direction doesn't look right, you just go flip it. Okay. So for example, what do I mean by flip it? You go to your load, double click. If you don't like this, you put a minus. Of course, it's going to be not what I want. You see that? It's not what I want. So double click, put it back to okay, positive 100. Yep. Okay, let's save our analysis, file, save management. Whoa, took a long time. Good, let's go ahead and run it. Done. So let's look at the deformation. You click on it. Isn't that what you expect? If you take a folded sheet metal like that, climb, you pressurize it, would it not deflect like that? Deflection looks like. And you can do animation. Now, of course, you notice that you cannot actually see the thickness here, but the thickness is built into the calculation. Okay, good. So I do number one. You want to see the deflection? Displacement, double click on it. You can change the color, the usual stuff. Change the rendering. There you are. So obviously the biggest displacement are in the middle. Now remember, this was a plane of symmetry, so there is a piece of structure on the left of this, and there's a piece of structure on the right of it. So this is the free, basically, edge. This is the free edge. In other words, this edge is free. That's why it deflects the most. It's right there. Okay? Now, you want to see the von Mises stress? You click on it, and you can see that the biggest stresses are, well, it depends with the places where the biggest displacement are, and this is where the cantilever position is. It's just like a cantilever beam, the biggest displacement, or sorry, the biggest stress is at the wall. Okay, this essentially is a wall for that. And same story, if you want to see the element, you just click on the on this rendering, and then you go to the last one, and the mesh elements or boundaries will show. Okay, good. Now, here is the number, 15,000 psi. Pretend that these numbers are all reliable. Let's go ahead and change this thing to parabolic and run it. Let's see how it looks like. Let's see what that 15,000 turns into. Activate the von Mises stress. Yeah, it goes to 17,000. So obviously, these are all numbers and colors, good-looking colors and numbers. You have to do a real mesh conversion study in order to develop any confidence for these guys, okay? Now, I want to repeat this problem, except that I don't want to extract the faces of that box, okay? Before I go any further, one of the assumptions that you have in shell theory, and this is extremely important, one of the assumptions that you have in shell theory is that the stresses through the thickness of the object, the thickness of the surface is zero. In real life, those stresses are not zero, may be very small. So shell theory obviously is not as accurate as the solid elements because of this, one of them is because of this assumption. So the assumption is that the stresses to the thickness, whatever the thickness is, for example, if the thickness is x, the normal stress in the x direction and the shears in the x. So sigma x, tau xy, tau xz are zero. If the thickness is direction is zero, sigma zz, tau xz, and tau yz are zero. Now, if you one way to see what's going on, if you go and say, hey, don't show me the von Mises stress, I want to see the principal stresses, and you zero in carefully, you see that it only shows you two principal stresses, which are both in that plane, and there is no stress in the third direction. It doesn't show you because we're using shell element. If this was solid, you'll see three of these arrows because there are three principal stresses. Here, there are two principal stresses. Anyway, so let's let me get rid of this. And let me get rid of that. I go back to my part. Okay. Because I'm just creating the surface and I'm not doing the box, so I can select this edge, and there are different ways of creating these surfaces. By the way, I select that vertical plane and I draw an inverted L like this, and I dimension it correctly. So this is 1, and that is 0.5, 0.5. Okay, here's what you got. So exit. So what I've done here for you is to draw this piece, this edge, 0.5 by 1. That's what you see right there. And I'm going to extrude it. Here's the way you create surfaces, the different ways. Simple surfaces, like what we have is extrude. This thing in by length of 2 inches, right? 2 inches. Because this was 4, half of it is 2. So I have created the surface directly. There is no box or anything. Okay. Let's apply material on this thing, and I don't have to join this. Because of the way I've done it, I don't have to join it. If I had created for example, a line here as a sketch, a line vertical as another sketch, and extruded both of them, it will look like that. But these surfaces, if I had done it that way, if I don't join it, there will be duplicate nodes along that edge. But because I put both of these lines in the same sketch, I didn't do two separate sketches for this edge and this edge and extrude. Because I did it both in the same sketch, there won't be a seam. You don't have to join. I mean, if you join it, you're not going to gain anything. That's all I'm saying. If you can join it if you want, but it's not necessary. Okay, so let's go ahead and apply material to this. Where is this apply material? I keep losing it. Right there. Metal, brass on that piece. We say okay. Now we're going to go to analysis and simulation, generative structure analysis. I'm not going to save these things anymore. We say okay. Now, notice that no three-dimensional element, CATIA did not see three-dimensional objects so that it jumps on it and meshes them, and did not create a three-dimensional property because there was no three-dimensional element. Now we have to do that. We don't have to delete anything here. Remember, in the first attempt that I made, it created a 3D property and 3D element that I have to go and delete. So here I just go and directly mesh, click on this, select that. Notice that I did not join, but it took both of them because of the way it was made. And I believe this is the size that we use. Okay, let's make it smaller, 0.1, parabolic, no problem. And the property we have to do anyway. So there's a 2D property. You select that. Because of the way it was done, everything is done at the same time. All right, so this is good. It's brass, thickness of 0.1. Very good. As you can see on mesh, by the way, you can see right click, mesh visualization. Mesh is created, but if you want to see it, it's right there. And then deactivate. Okay. The rest of the problem is pretty much the same. So you clamp this bottom edge. Okay. This was edge of symmetry, so you go to user define, uncheck all of these to make sure you don't make mistake. This is the edge that I want. That is in the ZY plane. As soon as it says ZY plane, no displacement in X. Rotations, opposites. Exactly what we did before. Another one, let's uncheck that. Notice that you can go and select, you cannot even select this because there's a sketch that it's sitting there. See that? There's a sketch. This white thing is a sketch. Why don't you hide that? And now you can select. Oh my God, I made a mistake in the previous problem. the first attempt. Watch out. First attempt. I made a mistake. I should have also taken that edge, vertical edge. I forgot. That's a lot of point deduction, on the test. Please, I lost my points. I just did these two. You have to do this vertical edge. Okay, be careful. When I post this thing, I'm going to make a comment that I forgot to take the vertical edge when I did it with the box. Okay. Now these two lie in the XZ plane. No displacement in Y. Rotations opposite, like that. And then we say, okay, very good. Um, yes. And pressure on that face, 100 psi. Now you may say, wait a minute, where is it? Well, because of the way you have done it, it's right there. You see this? It's right underneath. You don't have a control over that. That depends on how the surface was generated, basically. Double click on this, you put a minus sign to emulate exactly the same problem that you did before, minus. And now just that reverses it. It's the same problem. It doesn't matter whether you put it on the top or the bottom, because this is a surface. It's the same effect, but you don't have a control here. It is possible to do it so that these guys will end up on the top pointing down, which has the same effect, but I'm not going to worry about that. It has to do with the direction of the surface. You don't have to worry. Just watch your load, make sure that it points in the right direction, and it is right here. It is pointing in the right direction. Okay, good. And I'm not going to save anything. I'm not going to save these things, so we're going to run it. All right. Deflection or deformation is right there. Displacement right there. Double click on it. Average ISO looks like that. Still, pattern is the same, except that obviously the answer that we got previously was not right because of that. It may be close to it, but it was not right. Okay. If you look at the von Mises stress, 70, so you can see that the stress didn't change that much. Yeah, yes, this was not done correctly in the first attempt, but you can see the difference is not much. Okay, you don't want to make that mistake. Okay, all right. And once again, if you look at the principal stress right here, notice that it gives you depending on what point you look at it, they'll give you the arrows, two of them in plane principal stresses, because the out of plane one is 0. That's the assumption in the shell theory. Okay, stress through the thickness is 0, thin shell theory. Okay, good. Let me check a couple of things here, and that is I will. Let me go get my von Mises stress. Well, actually, let me go get my displacement, which I don't think I did. Did I? Oh, translation. Okay, let me deactivate this in case I ever need it. Activate translation. You can either say right click activate or just double click on it. Either way. Yeah, good. Now, notice that this is all blue. What that means is that the deflection is very small. By the way, this can buckle. We're not doing any buckling problem here. This is all static. Okay. And now, but I want to see, some color here. And I know there is color. It's just that these are so big that overwhelms that. So what you can do is let's deactivate this. And let's say we want to create a group. That's what the purpose of the group is. You go to the group toolbar right here. Toolbar. And one of them is group by surface, I believe. What is this one? This one is line group, surface group. You click on it and you say, okay, which surface do you want? I want this surface. We say, okay. activate your displacement, double click on it, click, choose the selections tab right there, see that selections tab? And say, just show me the group that I created. Where is that group? Surface group, right there. See that? Double click on it, right here. Okay? Because the deflection for that top piece was so much it had overshadowed these numbers. Now you can see, and of course this is the correct scale, okay? Associated with this stuff, very small deflection. The legend changed because you're only doing that portion. Now, if you want everything back, notice that, by the way, 0.0030199, biggest displacement here, which is that location. If you want everything back, just click on this. It's going to go back, and obviously it's going to be a lot bigger here. That's why this was all true. Okay, so that takes care of this problem. Now, remember, the different ways to create these surfaces. Just to convince you, I'm going to close this. I'm going to go back here. I'm going to go back here to that sketch and take away this. And exit. There we are. Back into that plane and sketch a vertical line going from there, normal view, zoom in, okay, going from there to there, and just to make sure it's right, I'm going to give this thing 0.5 as the thickness, not the dimension. Notice that 0.501 about 0.5, and okay, and exit, and extrude it, the same length. Now, when I go to analysis and simulation, generative structure analysis, static, I can mesh that right there. And look at your mesh. It only shows you the top because the side is not meshed. Deactivate this. Now you're going to go mesh it again. This side. You say okay. Now when you say show me the mesh, it shows you both. Good, good. Let me hide the surface, the actual surface. I want the mesh. Let me hide this surface, by the way. Hide this. If you zoom in, you put the cursor here. This element, for example, notice on the top along the seam, it's nodes 23, 124. When you look at the vertical one, the nodes are different node numbers. This is why if you do it like that and you actually pressurize the top face, these guys don't see each other, they have nothing to do with each other, and it will not run because this as if this will want to fly away. There's no restraint to hold it in that place. It will not run. I can guarantee you that. It will not run. Of course, it's possible to come and fix this, create a connection between these, and make that thing some kind of a rigid connection or fastening connection. And we're going to do some of those stuff later on, but this is not going to do it. The alternative would have been when I mesh this thing, it is possible to go and say under other, you mean under, you can't do it here, you have to go to advanced meshing tool. You say, if you see a node close by, within some tolerance, just merge me with that node. So it is possible to do things like that, but that's not where we're going right now. Okay, so that takes care of this. Okay, so let me get rid of that, because I want to go and do this problem for you. Okay. This is not to tell on, it's just that I want to show you that if you're a three-dimensional object and you want to put some pressure in a certain area here, and maybe a point here you want to apply a node, apply a load on it, what to do. Okay, that's what this is talking about. It says creating patches and points to be imposed on the mesh. Okay, let's go here. Start with part file. Dimensions are not important. So I'm gonna, because I want to be in three-dimensional object, I'm gonna go to part design right here, or from there, mechanical simulation part, mechanical design, part design, right? So on that vertical plane, I will sketch a rectangle, right there. Pretend this is the cross section of that box, and we're going to pad it to the length that we want. There we are. Now, I'm going to create a patch here where I want to apply a pressure, for example. And I want to create a point there where I want to put a concentrated for. Let's start with a point. For example, with a coordinate or on that surface, on this surface. There's the blue one. See the blue one? See the blue dot? So it's going to create a point there. You can see that right there. It's on that surface. And then I want to create a little patch here. So for example, I can say on that face sketch, once again, what do we want here? Ellipse? Okay, here's an ellipse. Where was that point, by the way? The point is on this side, right there. Here's an ellipse. Is that good? Exit. Now, although there is an ellipse on that, in order to create a patch here, we need to put a surface on it. Okay, so we go to, and there are other ways to do it, of course. So in order to, as soon as you say surface, you have to go to generative shape design, or from here, you go to start, shape, generative shape design. And there is an icon here. This is the way you make surfaces. We have already used extrude to do it. To do one. There is this thing which says fill. You click on the fill. Now, when you use the installation at the computer center, your dialog box here will look different. Because mine is an older version, it doesn't have all the features. But essentially, a fill. So I'm going to select. In your case, you're going to say inner boundary, outer boundary, etc. Just select that ellipse. You're doing a simple problem. You say okay. Notice that it did put an ivory looking color here. You can see that. You see this right there. So a patch has been created here, but that's not good enough. We have to sew this patch into that, or sew the surface into that object. And that, as soon as you say sew it into the three-dimensional object, you have to go back to part design. You go back to mechanical design, part design, back there. And then you see where the saw is. You see that? On the surface space feature, this is something called sew surface. So that surface, make sure the arrow points into the direction of the object that you want to sew it. You can click on the arrow, okay, and then you say, okay, good. All right. So let's now go to analysis and simulation, generative structure analysis, because we want to solve this problem as a 3D problem. I didn't put material there, but that's okay. There's no problem. As a matter of fact, you know what? Let's go back and put material on. So where is this? Material is somewhere here. Aluminum, for example, on that. Fine. And now we're going to go to analysis and simulation, generative structure analysis. CATIA sees a three-dimensional object and immediately meshes it. Okay. Now let's make the mesh a lot smaller so that I can see things. So for example, double click on that and I'll put down 0.1. If necessary, I'll make it even smaller. And I'll make it linear. So right click, mesh visualization. Okay. Okay. If you zoom in closely, we will be able to see that shell basically somewhere. So if you don't see it, right click on the part, say hide and show. Whoops, actually, you see it created the mesh, but it didn't go through those points. Okay, that's not good enough. So let me do the following. Something did not work out. Let me go back. Let me go back here to uh, part. Okay, and click on that. Click on that. So say simplify geometry. Simplify geometry. Simplify geometry. We say okay. We're going to go back to our mesh. Say okay. Hey, hopefully this ellipse will be taken into account. And let's check it now. Yeah, you see that? All the nodes are made to go through that. Without that simplified geometry, the mesh would not have been on that. Now, before I go any further, you notice something here, and that is, yeah, but that point is somewhere there. Okay? So here's what I'm going to do. I'm going to double click on this octave tetrahedron mesh. There is a tab here which shows local. See local, impose point at that point. So put a node at that point. We say okay, and now look at your mesh. One more time, double click on the mesh, or say activate, either way. Okay. So if you look close enough, you see that first of all, the ellipse is taken care of. The nodes are all on the boundary of the ellipse. And if you go to that node, that point there, yeah, you see, there is a node at that location. And this is why I can put a force there and I can put a pressure there. So let's go ahead and finish the problem. I made it linear because that element was too small and there's too many elements here. That's why I didn't want to make it parabolic. It will take a long time. Just to convince you, just double click on this thing, make the element bigger, 0.2. Everything must be taken care of again. So let me make it 0.2. Double click, let it mesh or activate the mesh. And if you look close enough, these elements are bigger, but again, the nodes must go through the ellipse and they are going. You can see that. And on this side, there must be a node at that location. And it is. You see, it takes care of that. Okay, so I think this is better. Now deactivate this, do the rest of the problem. So you tap this end, and you put a pressure on that face, and it'll take it, because there's a feature there. There, you see that? I'll put a positive here so it pushes in. And you apply a load to that point, and it'll take it. Now, if you don't see it, it's because of the rendering that's changed, because it's pushing it down. I bet if you what is it? I'll put in direction Z actually. This direction Z. And just so that you can see it, I'll put down positive, put a positive number. It does whatever it is, right there. Okay, so let's run it. It's going to be fast. Good. You can look at the deflection. Now, depending on what the pressure was, what the area was, and what the force was here, it may be going up or down. I don't know. This force is a lot bigger than that force imposed by the pressure. That's why it's going up. If you look at the stress right there, you can see that there's a big force here. That's why it shows. And there must be a stress distribution here. You can actually see that there's the ellipse. And if you do not want this thing to uh, do not want this thing to overwhelm that, what you can do is the following. You can create another group. So let's deactivate this plot. Okay, let me create the group. From laser making group, I'm going to create a group by surface group, for example. Now, I don't want it to be there. It's a resize it or change the location. I clicked on that ball there, and you can make it smaller if you want. You say OK. Double click on the one meter stress. I say, don't show me the whole thing on the selection. Say, show me the sphere group, and hide this. Hide that. It's right there. You can see that. So the purpose of a group is to zoom into a particular area and display things. One of the purposes. Now that takes care of this lecture. See you in class tomorrow. See you in the lab tomorrow, and you will be doing a shell problem. Okay?